Hi friends, here we discuss on contour integrals, that is integrals of complex valued functions of complex variable. The integral of a complex valued function f of the complex variable set is defined in terms of the values f of z along a given contour C extending from a point z is equal to z1 to a point z is equal to z2 in the complex plane. It is therefore a curve integral, usually called a line integral, and its value depends in general on the contour C as well as the function f. It is written as integral over C fz dz, or we can write it as integral z1 to z2 f of z dz. The notation integral z1 to z2 f of z dz is used when the value of the integral is independent of the choice of the contour taken between the two endpoints z1 and z2. This will be explained in the next session. Precise definition of line integral is that suppose the equation z is equal to z of t, that is z is equal to z of t. Here t varies in between a and b, a less than or equal to t less than or equal to b, equation number 1. This represents a contour C extending from a point z is equal to z of a to a point z2 is equal to z of b. Let the function f of z be piecewise continuous on C, that is the function f of z of t. F of z of t is piecewise continuous on the interval a less than or equal to t less than or equal to b. We define the line integral or contour integral of f along C as follows, that is integral over C fz dz is equal to integral over a to b. Instead of fz we have f of z of t into z dash of t dt. Equation number 2. Next we have the existence of this equation. Note that since C is a contour, z dash t is also piecewise continuous on the interval a less than or equal to t less than or equal to b. And so, the existence of the equation 2 is ensured. Next we have some properties of line integral. We now state some results, that is the first one is linearity. If z0 is a complex constant, first we have integral over C z0 f of z dz is equal to z0 into integral over C f of z dz. We can mark this as equation number 3. This is the first property or the first theorem. Next again we have this linearity, that is it is just like integral over C fz plus gz dz. Here we have two functions fz plus gz dz. This is equal to integral over C fz dz plus integral over C gz dz. Equation number 4. This is again linearity property. Associated with the contour C, which extend from the point Z1 to Z2 used in the integral 2 is the contour minus C consisting the same set of point but with the order reversed, so that the new contour extend from the point Z2 to the point Z1. That we can draw a figure, that is this is our x axis and the y axis, or we can say a real axis and imaginary axis. Here this is our Z1, this is our Z2, this is our C1, and again C2 is from Z2 to Z1, that is in the reverse order. This is our C2, it is from Z2 to Z1. Next we have sense reversal property or sense reversal theorem. It states that integral over minus C f z dz, integral over minus C f z dz is equal to nothing but minus integral over C f z dz. Equation number 5. Next equation. If C has the parametric representation, that is Z is equal to Z of t, a less than or equal to t less than or equal to b, then the contour minus C has the parametric representation Z is equal to Z of minus t, where this t varies as minus b less than or equal to t less than or equal to a. Sorry, here we have minus a. Thus, integral over minus C f z dz, which we can write as it is integral minus C varies from minus b to minus a f of z of minus t into z dash of minus t dt, where this z dash of minus t denotes the derivative of z of t with respect to t evaluated at minus t. After a change of variable in the last integral, we find that integral over minus C f z dz is equal to, this we can write as minus integral over C f z dz. Next we have a definition. Suppose that C consists of a contour C1 from Z1 to Z0, that I will draw. That is, C1 is a contour from Z1 to Z0, followed by a contour C2 from Z0 to Z2. That is, it is just like this. C1 is from Z1 to Z0, here we have Z2. C1 is a contour from Z1 to Z0 and C2 is from Z0 to Z2, Z0 to Z2. This is our C1 and this is our C2. The initial point of C2, that is the initial point of C2 is Z0, it is the terminal point of C1, that is the final point of C1. Sometimes the contour C is called the sum of its legs C1 and C2 as is denoted by C1 plus C2. The sum of two contours C1 and minus C2 is well defined when C1 and C2 have the same final points and is written C1 minus C2. Next theorem is partition of path. Suppose that C consists of a contour C1 from Z1 to Z0 followed by a contour C2 from Z0 to Z2, the initial point of C2 being the terminal point of C1. Then we have integral over C f z dz, which is equal to integral over C1 f z dz plus integral over C2 f z dz. This is our equation number 6. Suppose that C consists of a contour C1 from Z1 to Z0 followed by a contour C2 from Z0 to Z2. The initial point of C2 being the terminal or the final point of C1. Then there is a real number C where Z0 is equal to Z of C, such that C1 is represented by Z is equal to Z of T, A less than or equal to T less than or equal to C, and C2 is represented by again Z is equal to Z of T. Here T varies as C less than or equal to T less than or equal to B. Now by definition 2 we can write integral over C f z dz as integral over C f z dz as integral from A to B f of z of t z dash of t dt as A less than or equal to C less than or equal to B. Using result from calculus, we have integral over C f z dz is equal to which is equal to integral over A to C, it is from A to C f of z of t z dash of t dt plus integral over C to B f of z of t z dash of t dt. That is integral over C f z dz is equal to, here it is from A to C, it is our C1. So, I can write integral over C f z dz as integral over C1. This is integral over A to C f of z t z dash t dt. So, this I can write integral over C1 f of z dz plus this is nothing but integral over C2. It is integral over C2 f of z dz. This is equation number 6. Next theorem is that if W of t is a piecewise continuous complex valued function defined on an interval a less than or equal to t less than or equal to b, that is closed interval a b, then theorem says that it is modulus of integral a to b w of t dt. It is less than or equal to integral of a to b modulus of w of t dt. Over here a less than or equal to b. The proof is left as an exercise for you. Next we have a theorem, a named theorem, ML inequality. If M be any non-negative constant such that mod fz less than or equal to M everywhere on a contour C and L is the length of C, then says that modulus of, theorem says that modulus of integral a to b fz, it is not from a to b, we can take it as integral over c, integral over c fz dz. It is always less than or equal to ML. Question number 7. This is our ML inequality. According to definition 2 above, we have modulus of integral C fz dz it is equal to modulus of integral a to b f of z of t z dash of t dt by definition 2 and which is less than or equal to, I can interchange this as less than or equal to integral a to b mod f of z of t z dash of t dt using theorem 5. That is modulus of integral over c f z dz is always less than or equal to integral a to b mod f of z of t z dash of t dt. Since the values of f on c satisfy the inequality mod f of z less than or equal to m, then modulus of integral over c f z dz, which is less than or equal to modulus of integral over c f z dz is less than or equal to m into what remains, integral over a to b mod z dash of t dt. The integral on the right represent the length L of the contour C. So, hence from this we can write it as less than or equal to m L. This is the length of the contour. This is the proof. Next we have a remark. That is, equation number 7 is a strict inequality when the value of f on C are such that mod f of z is strictly less than m. Note that since all of the paths of integration to be considered here are contours and the integrands are piecewise continuous functions defined on those contours, a number m such as the one appearing in inequality 7 will always exist. This is because the real valued function, that is mod f of z of t, is continuous on the closed bounded interval a less than or equal to t less than or equal to b when f is continuous on C. And such a function always reaches a maximum value m on that interval by maximum minimum theorem for real valued functions defined over closed bounded interval. Hence, we can say mod fz has a maximum value on C when f is continuous on it. It now follows immediately that the same is true when f is piecewise continuous on C. We can discuss what is maximum minimum theorem for a real valued function defined over closed bounded interval. That is, let I is equal to closed interval a b. That is, it is a closed bounded interval and we are defining a function f, not merely a function, it is a continuous function f from I to R. Then f has a absolute maximum and an absolute minimum on I. That is what our theorem says that. Next we have definite integral in calculus can be interpreted as areas and they have other interpretations as well, except in special cases. No corresponding helpful interpretation, geometric or physical, is available for integrals in the complex plane. We can evaluate it, that is the first method of evaluation. Line integral by the use of the path. It is our theorem number 7. Suppose the equation, that is z is equal to z of t. Of course, t is in the closed interval a b. Mark it as new equation number 1. It represents a smooth curve C extending from a point z is equal to z of a to a point z2 is equal to z of b. Here our z1 is equal to z of a and z2 is equal to z of b. Let the function fz be piecewise continuous on C. That is, the function f of z of t is piecewise continuous on the interval closed interval a b. Then the line integral or contour integral of f along C is given by integral over C fz dz is equal to integral over a to b f of z of t z dash of t dt. equation number 2, where this z dash is nothing but dz by dt. Next we have some examples, that is to find the integral over c z square dz, where c is the line segment from z is equal to 0 to z is equal to 2 plus I. That is integral over c fz dz. Here our fz is, we can write it as fz is z square, and z varies from 0 to 2 plus I. This is our real axis, imaginary axis. It is from 0 to, here we have 1, 2, I, like that. It is a point 2 comma I. Z varies from 0 to 2 plus I. The curve C is like this. This is our curve. To find the equation of the line segment C, we first find the equation of the line passing through the origin, that is through 0, 0, that correspond to z is equal to 0, and 2, 1 that corresponding to z is equal to 2 plus I. And it is given by, equation is given by y minus 0 is equal to 1 minus 0 by 2 minus 0 into x minus 0. This is the equation. That is, simplifying, I can write y is equal to what? X by 2, or in terms of x, it is equal to x is equal to 2y. Hence, C is the line integral given by the parametric equation z is equal to 2y plus iy. Here y is in between 0 and 1, 0 less than or equal to y less than or equal to 1. This is our equation number 8. Instead of 8, one can take the following parametric equation also, as z is equal to x plus I into x by 2. Z is equal to x plus I into x by 2. Here x varies as 0 less than or equal to x less than or equal to 2. We note that the equation number 8 is a parametric equation in the parameter y. Hence, z dash is equal to dz by dy, which is equal to 2 plus I. So that dz is equal to 2 plus I into dy. Also, on C, z is equal to 2y plus iy gives z square is equal to 2y plus iy. Gives, no, it is 2y plus iy whole square. Z is 2y plus iy, here we have z square, it is 2y plus iy whole square, which is equal to, on simplification we get it as 3y square plus I 4y square. Hence, using the definition given by equation 2, noting that y varies from 0 to 1. Here, integral over c z square dz is equal to integral over 0 to 1 3y square plus I into 4y square into 2 plus I dy. On simplification, we get it as integral over 0 to 1 it is integral over 0 to 1 3 plus 4I into 2 plus I into y square dy. This on simplification we get 3 plus 4i into 2 plus I. They are constant, we can take outside. Integral over 0 to 1 y square dy. It is nothing but 2 by 3 plus 11 by 3 I. On simplification it is 2 by 3, or you can say 2 plus 11 I by 3. Next we have to find integral over c z bar dz, where c is the upper half of the circle, mod z is equal to 1. That is, here z is from minus 1 to 1. That is integral over c z bar dz. Here z varies from minus 1 to 1. Z varies from minus 1 to 1. That is the upper half circle. Here is our 1, here is our minus 1. This is our C, minus 1 to 1. Here C is given by z is equal to e raised to minus I theta. E raised to minus I theta. Of course, this theta varies in between minus pi less than or equal to theta less than or equal to 0. Hence, on C, we can take z bar is equal to e raised to I theta, and dz is equal to minus I into e raised to minus I theta d theta. And hence, integral over c z bar dz, we can write integral over c z bar dz as which is equal to integral, here it is from minus pi to 0, e raised to I theta, we have z dash of theta as minus I into e raised to I theta d theta. Here we have minus e raised to minus I theta d theta, which is equal to, we can take minus I outside because it is a constant, minus I into integral minus pi to 0. What remains? It is, here we have e raised to I theta and e raised to minus I theta. So, here we have only d theta remains, which is equal to minus I into integrating d theta, we have theta, the limits are from minus pi to 0. So, it is equal to minus pi I. Using theorem 3, the parametric representation for minus c is equal to, which is equal to that is minus c as z, which is equal to e raised to I theta. Here theta varies from 0 less than or equal to theta less than or equal to 2 pi. No, it is pi. That is minus e, z is equal to e raised to I theta, theta is in between 0 and pi. Hence, integral over c z bar dz, which is equal to minus integral over minus c z bar dz, which is again equal to minus integral 0 to pi e raised to minus theta I e raised to I theta d theta, again which is equal to minus pi I. Next example is to evaluate the value of the integrals, that is I is equal to integral over c z bar dz and integral over c dz by z, where c is the right hand half, that is z is equal to 2 e raised to I theta, where theta is in between minus pi by 2 and pi by 2 of the circle mod z is equal to 2. From z is equal to minus 2i to z is equal to 2i. That is, it is just like this. This is our 2i, this is our minus 2i. It is the right half. This is our C. It is in between 2i and minus 2i. It is of course the x axis, and again here it is the y axis. Solution is that according to our definition 2, we can write I is equal to integral minus pi by 2 to pi by 2 e raised to I theta bar into its derivative, that is 2 e raised to I theta dash d theta. Since e raised to I theta bar is equal to e raised to minus I theta and e raised to I theta dash is equal to I e raised to I theta, that is its derivative, we have I is equal to minus integral over minus pi by 2 to pi by 2 e raised to I theta into 2 I e raised to I theta d theta, which is equal to 4I integral minus pi by 2 to pi by 2 d theta, which is equal to what? It is simple but 4 pi I. Now, to evaluate the next one, that is integral over c dz by z, we note that when a point z is on the circle mod z is equal to 2, it follows that mod z square is equal to 4, which implies that z bar is equal to 4, or we can say z bar is equal to 4 by z. Hence, the above result, that is I is equal to 4 pi I, enables us to evaluate mod integral over c dz by z. We can say it as integral over c dz by z is equal to integral over c what 1 by 4 we have z bar into dz or z bar dz, which is equal to 1 by 4 integral over c z bar dz. That is, we can take 1 by 4 outside, that is 1 by 4 is a constant. So, integral over c z bar dz. It is again 1 by 4 into 4 pi I, which is equal to pi I. Next, to evaluate integral over c z dz, where c is the first quadrant of the unit circle mod z is equal to 1. From z is equal to I to z is equal to 1. That is, our figure is like this. It is in the first quadrant. Z varies from I to 1. Here it is I, this is our 1, like this. The parametric equation of the part of the circle is z is equal to e raised to minus I theta, which is equal to cos theta minus I sin theta, where theta is in between minus pi by 2 to 0. Also, dz is equal to minus I into e raised to minus I theta d theta. Hence, integral over c z dz, integral over c z dz, we can write it as integral, here it is from pi by 2 to 0, pi by 2 minus pi by 2 to 0, e raised to minus I theta into minus 1 minus I into e raised to minus I theta d theta. On simplification, it is equal to minus I into integral minus pi by 2 to 0 e raised to, here we have e raised to minus I theta and here we have e raised to minus I theta. So, it is integral minus pi by 2 to 0 e raised to minus 2 I theta d theta. On integration, we have it is minus I into e raised to minus 2 I theta by 2 I over the limits minus pi by 2 to 0, which is equal to 1 by 2 cos 2 theta minus I sin 2 theta over the limits minus pi by 2 to 0. On applying the limits, it is from minus pi by 2 to 0. On applying the limits to theta, it is equal to 1 by 2 into 1 minus minus 1. It is simply but 1. Next example is, we have to evaluate integral over c dz by z minus a. Where the c is a circle mod z minus a is equal to r oriented in the positive direction. That is, the given circle is like this. Centered at A with the radius r. We may write the parametric equation of the circle as z is equal to a plus r e raised to I theta, where theta is from 0 less than or equal to theta less than or equal to 2 pi. Hence, dz is equal to r I e raised to I theta and z minus a is equal to r e raised to I theta. Therefore, integral over c dz by z minus a is equal to integral over c dz by z minus a is equal to integral 0 to 2 pi r, our dz is r I into e raised to I theta divided by r e raised to I theta d theta, which is equal to, we can cancel e raised to I theta, so and r also, so which is equal to integral over 0 to 2 pi d theta I d theta, integral 0 to 2 pi I d theta. This I is a constant, we can take outside, and integral d theta we know it is theta. So, the answer is 2 pi I. Next example is, we have to find integral over c z minus a whole raised to n dz. We have to show that is integral over c z minus a whole raised to n dz. Not to evaluate, we have to show that it is equal to what? 2 pi I if n is equal to minus 1, and otherwise it is 0, that is when n is equal to n naught is equal to minus 1. Where n is equal to minus 1, we have to show integral over c z minus a whole raised to minus 1 is equal to 2 pi I, and in the other case z minus a whole raised to n, where this n is not equal to minus 1, the value is equal to 0. Where c is the circle, mod z minus a is equal to r, oriented in the anti-clockwise direction. The case when n is equal to minus 1, that is the first case, is already done, that is in the earlier example. We proceed in the same line. We may write the parametric equation of the circle as z is equal to a plus r e raised to I theta, 0 less than or equal to theta less than or equal to 2 pi. Hence, dz is equal to r into I e raised to I theta and z minus a is equal to r into e raised to I theta. Therefore, integral over c z minus a whole raised to n dz, which is equal to integral 0 to 2 pi r raised to n e raised to I n theta into, put a bracket here, into r I into e raised to I theta d theta, which is equal to I into r n plus 1, here we have r raised to n and here we have r raised to n plus 1 integral 0 to 2 pi, what remains inside that integral, e raised to I into n plus 1 theta d theta. Here by combining these two, we can, here it is e raised to I into n plus 1 theta d theta. This is equal to, this I can write as, which is equal to I into integral 0 to 2 pi d theta whenever n is equal to minus 1. Or I can write it is equal to, the value is equal to I r into n plus 1 integral 0 to 2 pi e raised to I into n plus 1 theta d theta whenever n not equal to minus 1. that is the value which is equal to 2 pi I when n is equal to minus 1, and here it is 0 if n not is equal to minus 1. Since for e raised to I into n plus 1 into theta by I into n plus 1 over the limit 0 to 2 pi, the value is equal to 0. The next example proceed as in the previous example, that is integral over c dz by z minus z naught raised to n minus m plus 1. The value is equal to 0 whenever m not equal to n, and the value is equal to 2 pi I when m is equal to n. Next we have integral of a non-analytic function that is dependent on path. That is the example where the value of the integral depend on the path. In this example, where value of the integral depends on the path, we first let C1 denote the contour OAB, that is this is our A, here we have B, this is our C1, and we can mark this as our C2. Here it is I 1, so the point is 1 I, this B point is 1 I, and evaluate the integral over C1 f z dz as integral over OA f z dz plus integral over AB f z dz. That is integral over C1 f z dz. We can take it as integral over OA f z dz plus integral over AB f z dz. Question number 8. Where this f z is equal to y minus x minus I 3x square, that is z is equal to x plus I y. On the leg OA, x is 0 and y varies from 0 to 1, and hence its parametric representation is z is equal to 0 plus I y, where 0 less than or equal to y less than or equal to 1. And since x is equal to 0, at points on that leg, the value of f vary with the parameter y according to the equation f z is equal to y, where 0 less than or equal to y less than or equal to 1. Consequently, noting that dz is equal to I dy, we have integral over OA f z dz is equal to integral over 0 to 1 yi dy, which is equal to I into integral over 1 y dy, which is equal to I by 2. So, it is equal to I by 2. On the leg AB, y is 1 and x varies from 0 to 1, yielding the parameterization z is equal to x plus I, where 0 less than or equal to x less than or equal to 1, and so noting that dz is equal to dx, we have integral over AB f z dz as integral over 0 to 1 minus x minus 13x square dx, which is equal to integral 0 to 1 minus x dx minus 3I into integral 0 to 1 x square dx, which is equal to 1 by 2 minus I. In view of equation number 8, we now see that integral over C1 f z dz is equal to, that is integral over, here it is integral over AB, the value is 1 by 2 minus I. So, integral over C1 f z dz is equal to is equal to 1 minus I by 2. Equation number 9. If C2 denotes a segment OB of the line y is equal to x, that is this is our C2, with parametric representation z is equal to x plus ix, 0 less than or equal to x less than or equal to 1, noting that dz is equal to 1 plus I dx. Integral over C2 f z dz is equal to integral 0 to 1 minus I into 3x square into 1 plus I dx, which is equal to 3 into 1 plus I into integral 0 to 1 x square dx, which is equal to 1 minus I. Equation number 10. That is, we can write it as integral over C2. Integral over C2 f z dz. It is 1 minus I. Equation number 10. Evidently, then the integral of f z along the two paths C1 and C2 have different values, even though those paths have the same initial and the same final points. Also, we note that the value of the integral of f z over the simple closed contour, that is here it is O, A, B. This is our figure C1, this is our C2. That is, over the simple closed contour OABO or C1 minus C2 is integral over C1 f z dz minus integral over C2 f z dz, which is equal to 1 minus I by 2 minus 1 minus I by 2 minus 1 minus I. It is equal to minus 1 plus I by 2. The next example is integral of a non-analytic function dependence on path. That is, we have to integrate f z is equal to real part of z, that is x, from 0 to 1 plus 2i. Here we have two paths. Zero to 1 plus 2i. This is our C1, our C2, and this is C star. That is, we have to integrate along C star and along C, that is C consisting of C1 and C2. This is the point 1 plus 2i, and this is C1, 1 to 1 plus 2i, it is C2, and 0 to 1 plus 2i, that is our C star. Solution says that the parameterization of C star is given by z of t is equal to t plus 2it. Hence, that, and also this t varies in between 0 and 1. Hence, z dot t, which is equal to 1 plus 2i, it is nothing but the derivative. Z dot t is equal to 1 plus 2i, and f of z of t is equal to x of t on C star. F of z of t is equal to x of t, that is real part, on C star. Thus, integral over C star real part of z dz is equal to integral over C star real part of z dz, which is equal to integral 0 to 1 t into 1 plus 2i dt, which is equal to 1 by 2 into 1 plus 2i. On simplification, it is equal to 1 by 2 plus I. That is, the value is equal to 1 by 2 plus I. Integral over C star. The next one, we now have C1 is equal to z of t, which is equal to t, and of course c dot of t is equal to 1, that is again the derivative. We denote c dot as z dot as derivative, and f of z of t is equal to x of t, which is equal to t, where t varies in between 0 and 1, and c2 is equal to z of t, which is equal to 1 plus it, again z dot t is equal to I, and f of z of t is equal to x of t, which is equal to 1, 0 less than or equal to t less than or equal to 2. Thus, integral over C real part of z dz is equal to integral over C1 real part of z dz plus integral over C2 real part of z dz. which is equal to integral on C1, it is integral 0 to t 0 to 1 t dt plus integral 0 to 2 1 into I dt. It is equal to 1 by 2, the value is 1 by 2 plus 2I. Note that this result differs from the result in A, that is differs with the part A. Next example, where value of the integral is independent of the path. We begin here by letting C denote an arbitrary smooth arc z is equal to z of t, a less than or equal to t less than or equal to b, from a fixed point z1 to a fixed point z2. In order to evaluate the integral, that is I is equal to integral over c z dz integral over c, that is I is equal to integral over c f z dz, which is equal to integral a to b z of t z dash of t dt. We note that d by dt of z of t whole square by 2 is equal to 2 into z of t into z dash of t by 2, which is again equal to z of t into z dash of t, that we all know. Thus, we can write I is equal to z of t square by this square is for the z of t square by 2 over the limits a to b, which is equal to z of b whole square minus z of a whole square by 2. But we have z of b is equal to z2 and z of a is equal to z1. And so, I is equal to z2 square minus z1 square by 2. Z2 square minus Z1 square by 2. This shows that in this example, the value of the integral depend only on the end points of C and is otherwise independent of the arc that is taken. We may write integral over Z1 to Z2 Z dz is equal to Z2 square minus Z1 square by 2. That is, we can write it as integral Z1 to Z2 Fz Z dz. Fz is z. So, integral z1 to z2 z dz is equal to z2 square minus z1 square by 2, equation number 11. Compare this with the previous example where the value of an integral from one fixed point to another dependent on the path that was taken. This expression 11 is also valid when C is a contour that is not necessarily smooth, since a contour consisting of a finite number of smooth arcs Ck, where k varies from 1 to n, joined end to end. More precisely, suppose that each Ck extend from Zk to Zk plus 1, then we have integral over C Z dz is equal to we can write this as, which is equal to sigma, that is summation k varies from 1 to n, what, Z k plus 1 square minus Zk square divided by 2, which is equal to Z n plus summation, it is from 1 to n, it is equal to Z n plus 1 square minus Z1 square by 2. That is our equation number 12. It is Z n plus 1 square minus Z1 square by 2, equation number 12. Z1 being the initial point of C and Zn plus 1 its final point. It follows from this expression that the integral of the function, that is fz is equal to z, around each closed contour in the plane has value 0. Once again, compare previous example where the value of the integral of a given function around a certain closed path was not 0. The question of predicting when an integral around a closed contour has value 0 will be discussed in the next several sessions. That question is central to the theory of functions of a complex variable. Hope you enjoy the session. See you next time. Till then, take care.